My name's Allyson Klein, and today I am delighted to be joined by a visionary in the tech industry, Gary Smerdon, CEO and founder of MEXT. Gary, why don't we just go ahead and introduce yourself and a little bit about MEXT just to kick us off?
Great. Well, first of all, thank you for having me on. I really appreciate it. So, Gary Smerdon. I've been in the technology industry for a few years now, and MEXT is a company that we're focused on memory extension. You can think of the name MEXT, memory extension. And I'll get into kind of what led to the founding of the company, but basically we've seen an opportunity around challenges in memory, and so that's what got us started.
Now, we met each other a few weeks ago at Synopsys Converge, which was a fantastic conference to meet people. And, everybody was talking about how we deliver more compute power to large-scale challenges. But you have really been focusing on a quieter crisis that's going on within data center and edge environments, which is memory and memory scale. What was the aha moment that led you to realize that we were kind of looking at the wrong bottlenecks and that we needed to broaden our focus into the memory complex?
Yeah, so if you had to pick one moment, it's when realized in kind of the 2023, 3 years ago, that DRAM memory had become half of the cost of a server. Half. So, and then when we looked at it further, basically, we also realized that not only was it half, but when you looked under the hood, much of this memory was actually being poorly utilized. We saw studies from Meta, from Google, from Facebook, and Azure, which all highlighted that memory was really, while it was an expensive resource, we had as much as half of it or more that wasn't being utilized well. So put another way, more money was being spent on DRAM and wasted on DRAM, than was being spent on processors to Intel, AMD, and ARM combined. So that was like, okay, this is a problem. Can we do something about it? And that's what kind of led us to start studying this problem in more detail.
It's interesting. One thing that I think about with memory, and I've spent some time in the memory industry, is that this is a really unique time for memory. And it's a time where, a memory crunch could last for a decade. How did the industry so undercall the demand for memory scale with AI? And why is that hitting data centers so hard?
Yeah, so, the overall problem with memory, it's kind of been a train wreck. This has been taking place over a long period of time. It didn't just happen, in December of this year. It really goes back to, I would even say the problem started 50 years ago, where if you look at DRAM, it was first brought out in 1970 by Intel. And we've seen it in the marketplace essentially unchanged for decades. And what I started to study and look at 15 plus years ago is that memory was coming to the end of its life relative to being able to scale. Moore's law had been a critical part of that scaling, and that was coming to an end. And so basically, it wasn't going down in cost. We weren't getting devices with more memory on it. And now, all of a sudden, when there's a new opportunity around AI that's taken a lot of the capacity from the industry, the industry hasn't been able to respond, and it has become a big, big crisis.
Now, you've mentioned that memory can now account for up to 90% of a server's cost, which is crazy. Now, I know that the memory industry has worked on things like HBM to help address these low latency memory requirements for systems. Why hasn't that been enough to solve the capacity demand or at least unlock this market so that things were a little bit more in balance?
Yeah, so it actually, HBM is just accelerating the problem. And so when you look at DRAM, and HBM is actually just a specialized form of DRAM to give us high bandwidth, so more performance to really feed the pipelines of GPUs. But the technology is built in the same fabs as mainstream DDR5 is the current generation of memory that's used in PCs and servers. So they use the same fab. So it's actually taking capacity away from mainstream DRAM. But it's even worse than that. The bit per wafer of HBM is on the order of 1/3, maybe even 1/5 of DDR. And so every wafer that you are using for HBM, you're taking away from the capacity for standard DRAM in the marketplace at that 3-to-1, 4-to-1, 5-to-1 ratio.
Okay. Now, today came a big announcement from you guys. You're announcing a major milestone in what you call predictive memory. Can you give us just the synopsis of what this software change is and what it represents in terms of capabilities for enterprises?
Yeah, so let me kind of hit on a little bit more about what we saw and what led to this. So again, we talked about the memory challenge that was taking place, and then we really set out with 3 objectives that if we could achieve those, then we could have something special. The first one was that we needed to increase DRAM utilization. I mentioned the studies from Meta and Azure and others that said we had poor utilization. So we wanted to have really improved memory utilization, number one. Number 2 is that we didn't want hardware or software changes. The reason is that anytime we have hardware software changes, we are slowing adoption, we're increasing risk, but we're also increasing cost. So, and cost has been one of our biggest focus from the very beginning. And then the third one is that what if we could do something really special? What if we could bring flash, which is a storage technology, and make it appear as memory to the processor, to the operating system and application? Now, that is, you might ask, why is that important? Well, it's 50 times cheaper per bit. It's 30 times lower power per bit. There's just one little problem, and that is it's also 500 times slower. So that's what really the industry kind of got caught up on, is that this is a storage technology. It's not a memory technology. And that's what inspired us to really work the problem. We worked it, and that's where we came up with the foundation that the company is based on, that we call predictive memory. And it's a pretty simple concept. What we do is that a processor wants to work out of its caches. That's where it's getting the most performance. If it's not there, it wants to work out of DRAM. And then pages can kind of get cold. And what we do when those pages get cold, we are able to push those off into flash, into NVMe flash, literally with no impact on performance. Why is that? Because these pages aren't being touched. They're cold. They're not needed. So there's no impact on performance. That's the easy part. The hard part is you get no warning. A page goes from being cold to being hot in one instruction. So a fraction of a nanosecond. All of a sudden you need those pages. And now the processor is stalled. Everything's come to a stop while you're waiting for those pages to be pulled from back from flash. What we came up with the idea of is what we call predictive memory. And it's an AI engine that is monitoring what's happening in the system and continually training and inferencing, or what we call predictions. It's predicting and pushing back into DRAM the pages that it believes are going to be needed in the future. So this was a really interesting idea. It inspired us to start to research it. And we found, you know what, we could actually do this. We could predict accurately what was going to be needed in the future and push it back before the application of the operating system ever needed. And that's what allows us to transparently bring flash into the memory tier.
Now, this is super interesting because you're using AI to solve a problem that's created by AI. But let's go a little bit under the covers and, how is it actually driving these predictions? And, obviously, one of the thoughts that I have is, how do you train this algorithm to really understand what the application will need before it even asks for it?
Yeah, so we looked at many different AI models and trying to see what would work well, how can we achieve the performance we need. And what we ended up on is actually it's an ensemble of models, so multiple models. That's just a fancy term for several models working in concert with each other. But the workhorse is a transformer-based model, so the same as ChatGPT and all the other famous LLMs. So this transformer-based model is able, in our case, do something very different, though. It's making predictions in real time. It's also training in real time, because when we think about, ChatGPT, you hear about this training phase that can take days, weeks, months, and then you do inferencing, typically on different hardware after that. We are doing continual training. We don't pre-train. We start training right away, and then we make continual training. Why is that important? because there's thousands of applications out there. So doing a special training for each one is not practical. But the other thing is that the behavior of an application can change while it is running. So if you don't retrain, if you're pre-trained, you could get stuck in a non-performant way. That doesn't meet the end customer's goal. So we do continual training, and then we make continual inferencing. Again, we call those predictions. And we're doing that all on a single x86 or ARM core. So a lot of innovation there to be able to achieve it. Let me just touch on one other point. Regarding the training times, people go, well, how long does it take? And we actually begin making very good prediction in a matter of a few seconds.
Now, one of the most striking claims about reviewing your technology is that you have OS transparency. How do you actually make the OS and application think about flash behaving like expensive DRAM without any notice of the difference?
Yeah. So it's, part of the goals that we set out, I talked about no hardware or software modifications. And so to require no software modifications, what that really meant is that we needed to have just a driver, standard Linux driver. Linux is the operating system that we support today. And in addition to that, in user space, that's where we run our AI engine. So that's where we're running the AI model on a separate core. So what the application sees is the combined memory of DRAM plus however much of the flash we have provisioned as DRAM, or as, I shouldn't say it's DRAM, as memory to the system. So we take, for example, a 1 terabyte DRAM system, we add flash to it, our predictive memory software, and our default would all of a sudden be to have a 2 terabyte instance. But you can also make that smaller if that's what you choose, or you can make it larger. You can make it a 3 terabyte or even a 4 terabyte system. Again, all off that base platform.
Now, your data shows that you can actually quadruple memory capacity while having the cost of the system. Can you talk a little bit about what that means from an ROI perspective, and what have early customer responses been to this?
Yeah, so really our focus from the very beginning is around performance per dollar. And so performance per dollar is just, a fraction. Performance, divided by basically the cost effectiveness of it. So from a performance standpoint, and this, by the way, is the same exact model that drove VMware virtualization, where VMware set out to, of course, improve utilization of CPUs. We're wanting to increase utilization of memory. So again, what we do is, from a performance standpoint, what we typically see is that we are seeing 0.9, 0.95, 0.99, even 100% of the performance. And from a cost standpoint, we're able to reduce that in half or reduce it even more, given the tremendous escalation that has taken place in memory and thus server costs. So the equation, what we typically see from a performance per dollar, when you do the math on it, is 2x, 2.5x, 3x are common numbers. Now, you asked about customers and what are customers experiencing. This is what they're experiencing. It's been off a wide range of workloads and use cases, but what they're seeing is that they can install this in a matter of minutes. They can try it out. They can do side-by-side testing, and they're seeing the results that we're talking about. Now, there is another case in which you can actually increase your performance, and that's where you need more memory, because if you don't have enough memory, you're having to shard your data across multiple systems. A lot of other complexity comes into play. What we are able to do is allow all of that data, everything to be put on a single system, and thus actually increase the performance that or the time that a job takes.
Now, I know that there's going to be some skeptics in the room, so I'll just ask, if you're running a large LLM or a massive vector database, what's the actual performance trade-off when moving from DRAM to flash in this model?
Yeah, I mean, there's always your performance can vary, right? Any type of virtualization technology or any other of these things, if anybody says guaranteed, then that's just not intellectually honest. But what we're seeing customers experience is what I talked about, where they're achieving, essentially the same level of performance while reducing their costs by this significant amount. And often what that means, by the way, is that they're able to run 2 times or 3 times as many jobs simultaneously, and thus actually improving their time of getting their their product to market or whatever their particular business application is. Again, one of the things that we just encourage customers to do is try it. And with our technology, you can try it on premises. You can try it in the cloud. We've worked very closely with AWS, with Google Cloud as well, and so we run there all the time. But we also work on the other cloud providers as well.
Now, your co-founder David Reid, fun fact, helped build the internet. How does that deep systems perspective influence the way MEXT approaches modern data center problems?
Yeah, so David's a very unique individual. David is one of those people that is truly an expert. Everything from deep under the Linux, into the Linux kernel, all the way up to hardware systems, and even into the applications. Having been an SVP at SAP, working on HANA, et cetera. So he is a true savant across multiple things, and so we've had the great privilege to work together in the founding of this company. But we also brought in a lot of other really talented people as well. Carl Waldsberger is our chief scientist. He was employee 60 at VMware. He led innovation there for a decade, has close to 250 patents to his name, and is a well-respected, innovation expert. Let's see. Fred Weber. Fred Weber was our first advisor and has given us great advice through the years and pointing us in good direction. And he was the CTO of AMD in creating the 64-bit x86, leading to that innovation. And so is another well-respected expert. And we have a team of that. Everybody wants to say, listen, I have a team of rock stars. We do have a team of rock stars, many of which are in the Hall of Fame.
One question that I have for you is, you talked about how you're on-prem, you're in the cloud. We met at Synopsys, so I'm really curious about, the workloads around, chip design and simulation tend to be incredibly memory intensive. How do you approach that space?
Yeah, so EDA is an amazing use case for us. And let me touch on some of the things that are happening from an industry standpoint, which are driving it, and then it's led to our success there. So number one is that, we know everything happening with AI. We know there's this huge push in the industry to get, more advanced devices out at even faster cycles. And while doing that, these devices, of course, are getting incredibly more and more complex. And not only are we talking about chips, but we're talking about chiplets. And we're not only talking about chiplets, we're talking about, whole systems that all have to be simulated and really optimized simultaneously. And that was a big part of that particular conference, talking about how this integration and testing is to take place across multiple ways. So EDA is historically a memory-intensive workload, but it's been taken to another level of late. And so what we're doing is basically allowing huge systems to be created, allowing for less sharding of the data. I talked about that before. So we don't have to break the device into as many parts, which allows for a better device. It allows for a device that doesn't have to be optimized in little blocks. It can be optimized at larger levels. So we get better devices. We get them faster because we are removing steps as far as from the sharding of the data standpoint, and allowing more workloads to be tested simultaneously. Jensen actually at that particular show talked about how AI is causing us and giving us the ability to run more and more simulations, more and more place and route, all these other things that take place from an EDA standpoint, and to do that simultaneously or to do more of those in parallel. And of course, that's what we're doing is allowing these systems to be developed cost effectively, because compute has become the bottleneck. It's not the licenses, it's compute that is the bottleneck to running these workloads. And when I say compute, I'm talking about, of course, processors, memory, and the whole computing system.
Now, if MEXT scales as planned, what is the ripple effect on the supply chain? And does this take the pressure and constraints off of the major memory fabs at this point?
Yeah, so let me go back to a point I hit on before as I answer your question. So I talked about Moore's law coming to an end relative 15 years ago, and what do I mean by that? I mean this technology of one transistor, one capacitor, which gives us a bit of data. That cell size has not really changed in 15 years. So go back again to 20 years ago, you'd spend $1 billion, build a fab, and the fab capacity doubled after 2 years because a new process technology came out. Moore's law allowed us to shrink it. We doubled the capacity. 2 years later, we double again. Before you know it, you go 2, 4, 8, 16, even 32x the bit capacity from the same fab. That's what drove the economics from a memory standpoint. But that came to an end. So what happens today? You build a fab, you spend 30 or 50 or $100 billion on building your fab. The bit capacity is what you start with, is what you end with. So the economics have just been shattered when it comes to DRAM. And of course, what's happening in the world of data? Of course, we have more and more data and everything else taking place. And then, of course, we talk about HBM, and HBM is coming in and actually eating away from the capacity that we have for DRAM. So, and standard DDR5. So all of this has created a problem that is going to be around for a long, long time. Do I believe that MEXT and our predictive memory software is going to ease the pain? Absolutely. Do I think it's going to, but the industry and this is going to be something that is that we are bringing great relief for. It needs it badly. It is a hair-on problem, fire, and so I think we will help in a significant way. But the industry needs things desperately, as I described.
Now, looking 5 years into the future, do you think that this is going to be the predominant model across every server shipped?
I do. And I think it'll go beyond servers as well. It's as simple as this, right? Every technology in a computer has gone through not only major revolutions, a microprocessor. Intel came out a year after DRAM. They came out with the 4004 4-bit single chip microprocessor. That, today's processor looks nothing like that. But all the other parts of the system have changed dramatically. DRAM specifically hasn't. And all these other areas of a computer have tiering. They have different levels of performance. They have, of course, storage is an easy one to point to, where you can have different levels of performance and transparent tiering and storage layers. We need transparent tiering of memory layers. The industry, this is not a new idea, by the way, to do tiering of memory. Tens of billions of dollars has been spent trying to do this. Famously, Intel with their phase change memory technology, which they branded as Optane, tried to do this. And so people have tried before. It's just that the combination of hardware technology, in this case, flash, and software technology in the form of predictive memory and AI power is come together to bring a solution that the industry needs. So yes, it's going to be there. It's going to be widespread. It's the future of memory.
Gary, it's been delightful to have this conversation with you. I'm so excited about what's coming at MEXT. For someone who worked on 3D cross-point memory, both at Intel and Run, I'm excited to see a new entrant of technology enter the fray that can help address a challenge that has been longstanding in compute systems. Where can folks find out more about MEXT and engage with your team?
Yes, so we have quite a bit of information on our website, as well as the ability to connect to us directly there. So it's MEXT, MEXT.ai, MEXT.ai.
Thank you so much for being on today. I am sure that our audience is going to be acutely interested in what you and the team are doing.
Well, Allyson, it's been a pleasure. Thank you for having me on, and we look forward to engaging with your audience.